Hello, good morning.
Morning.
Okay. So, yesterday you people understood how to delete from the binary tree. Okay. There are three cases: deleting the leaf node, and then that is the simplest one, and deleting a node with one child, either the left or the right child, and then the third case is deleting a node with both the childs, left child and right child. And when you are performing deleting a node with one child or deleting a node with two childs, okay, uh, you got to write before deleting. You got to write the in order traversal of the given tree, and while deleting, you should go for replacing the node which is the node which is before the node which you are trying to delete, okay, in the in order traversal. So that is what we understood, and after that we understood um, how to what is a threaded binary tree. Okay, when a binary tree has more number of null links, okay, so we can convert them into the threads by building a threaded binary tree. And uh, you understood in the previous class how to write or build a threaded binary tree with an example. Okay, well, let me go there just. And I had asked you to construct the binary search, sorry, threaded binary tree for the other things as well. Okay, so this is the example that we understood in the yesterday's class, and this was the tree given, and for that tree, for this tree, we wrote the in order traversal, and here since the left link exists, okay, for B, the left child exists, okay, it is a non-null pointer, and here also both left and right are non-null pointer. Now if I take this case, okay, the H, left and right both are null pointer, and for H I cannot create a thread because before H I don't find any what node. Okay, before this, there is no node, hence it is a dangling pointer. And similarly, the right link of H, okay, again I can create a thread from H to D. Okay, so that is after H I have D, so a thread is created. What does it mean is from the right link of H you can get back to D, something like this, and this is how you can go for creating a threaded binary tree. And the same thing is here. Okay, a memory representation of a threaded binary tree. So how do we represent this? As we wrote it just like that without considering the memory representation. Now if I am going for a memory representation, how do I represent it? It is represented something like this. So data structure for threaded binary tree, so left thread, so here I have right thread. Okay, so if the left thread exists, I'll make it as true, and if the right thread doesn't exist, I'll make it as false. And similarly, this is the pointer which holds the pointer to the left child of this particular node, and this holds the address of the right child of the or right subtree of this particular node. And this is the info field which holds the information field. Now you can have a look into this structure. Okay, totally how many things we have here? 1 2 3 4 5 fields are there. Now we have created a structure with the name threaded tree, and inside this threaded tree I have left thread. This is the one. If the left thread exists, then this will be made as true. Okay, and then the threaded pointer left child, okay, this one, which points to the left subtree of this particular node, and then the actual information field, character data, this is the information field, and similarly threaded pointer the right child, which will hold the address of the right child, and the last one is short int right thread. Okay, which will be set to normally true if the right thread exists. Okay, this is the simple data structure for representing a node in the threaded binary tree. Okay, now this example same as this, but written in the form of a memory representation. Okay, this is the root node which I consider, or sometimes you can also call it as a dummy node. Okay, F and F I'm writing initially. Okay, since there is no thread here. Okay, and here also there is no thread. Okay, and this is the left child for this particular node. Okay, it is holding, or else you can also say, instead of me calling this as the root node, I can call this as a dummy node or the starting node, and this is the root node. Okay, just observe this. Okay, this is the left child and this is the right child. As usual, it is holding the address of the left child and this is holding the address of the right child. Since we have both the left child as well as right child present for this particular node, we have set the left thread and right thread boolean values as false and false. Okay, now I come to this node B. So this B also has got two childs. It has left child as well as right child. If you just look into this field of B is holding the address of the node D, and this field, the right field of B, is holding the address of the node E. Okay, and if you just look into the thread left and thread right, so both are set to false because, okay, sorry, here both are set to false. Why they are set to false? Because B has got both left child as well as right child. Okay, now if I take this node D, again it has got both the left child as well as the right child, hence the boolean thread left and the thread right are set to false. Now you take this the right child of B. Okay, right child of B, so doesn't have the left child or the right child. So it doesn't have the left child or the right child, and you can see the boolean thread left and the boolean thread right are set to true. Okay, now why they are set to true? Because a thread exists for this particular node, and here this is, instead of making it as a null pointer, we are storing the address of what? B. So you got to write the inner order representation of this particular tree. If I'm writing the inner order representation of this particular tree, what comes before E is B. So there is a thread from E to B, left link of E to B, and similarly even there is no right child for this E. If you are observing, OP people are following and able to understand what I'm saying? Okay, so similarly there is no right child also for the node E. It is represented as T. That means the thread exists for this, and when you write the in-order traversal for this particular tree, what comes after E is A. So the right link of E is directly pointing to A, and similarly all others are written. Now if I take this, okay, the leaf node H, which is the left child of D, so again there is no left child and right child for this particular node. You can observe both the left and the right thread fields are set to true and true. That means the thread exists, even the left thread exists for this child, and the right thread also exists for this particular child of the node D. Okay, and where, so before H we have this. Okay, see here when I say H, instead of see earlier in my previous example, for H it was a dangling pointer, correct, right? So I think this, let me copy it. So this is the in-order traversal. It was a dangling. No, I don't want the dangling pointer. Okay, so I just create some dummy node before the root node. Let me paste it here. This is the in-order traversal. So if you just observe now, for H there is no node before. Now what instead of just leaving it null and making it as a dangling pointer, now I'm putting a reference toward the dummy node which I'm creating. My actual root node is starting from here, but this is a pointer which is set back to the dummy node. Okay, and similarly the right link of H is set. See, after H we have D, so this right link of H is made to point to D. Okay. Now if I take I, okay, you can just observe here the left link of I. So before I we have D, so it is pointing to D, and the right link of I, so after I we have B, so it is pointing to the node B. Okay, you can just observe, follow this line, it is pointing to the node B. Now you observe here again G. Okay, the left link of G is set to point back to C, because before G what we have is C, but after G there is nothing. Okay, now when there is nothing, even you can avoid this dangling pointer by creating a dummy node, something like this. Is that clear? So this is the dummy node created, and the right link of the node G is made to point back to the dummy node that is created. So before starting with the actual root node, so we take a dummy node just to prevent these two dangling pointers what you get. So any binary tree you take, so there will be two dangling pointers. Okay, so to avoid these two dangling pointers, you can go for having a dummy node, and instead of leaving those dangling pointers with null values, so you can just point them, make them point back to the dummy node. See, once you reach this dummy node, again it is possible for you to get into the root node and traverse anywhere. Okay, so this is how the binary threaded binary tree is represented inside the memory. So you require totally 5 fields for doing so. So one, the two boolean values, the outer ones are the boolean values, thread left and thread right, and the middle two are left child and right child, and the middle one is the actual data or the information field. Okay, so now I'll give you an example. I want you people to just build a threaded binary tree, so in this form. Okay, by using the memory representation, where each node is represented by using 5 fields. Okay, I'll give an example right now. Okay, let me make it full screen. So now threaded binary tree for this, I'll take 10, 8, 6, 12, 9, and then 11, and then 14. Okay, now start writing for this. With this sequence, you build the threaded binary tree. So first you construct the normal binary tree. Okay, so 10, before 10 I'll take some dummy node. Let me call this as dummy node, DUMMY, dummy node. Now under this dummy node I'll write my actual root node 10, and then so 8 is the next node. Since 8 is less than 10, it gets inserted towards the left side. And next is 6, I compare that with 10, it is lesser. And again I compare that with 8, it is still lesser. It gets inserted towards the left side of 8. Next 12, it is bigger than 10, it gets inserted towards the right side. Next is 9. Okay, compare that with 10, 9 is less than 10, comes here, but 9 is bigger than 8, so it gets inserted to this place. And next is 11, 11 is bigger than 10, we come here, but 11 is lesser than 12, it gets inserted as the left child of 12. And then 14 is bigger than 10, and 14 again, it is bigger than. Please mute. Please mute. Okay, so 14 is bigger than 12, it gets inserted towards the right side of 12. So this is what the binary tree constructed. Okay, now you have to write an equivalent threaded binary tree for this. Now before writing the equivalent threaded binary tree for this, we will try to write the in-order traversal for this. In-order traversal. Tell me the in-order traversal for this. So leave this dummy node. Dummy node is, don't take this into account. Just start telling me the in-order traversal for this. Start it fast. 6, 8, 9, okay, 10, 11, 12, 14. Okay, this is the in-order traversal we have written. Now we'll start writing the threaded binary tree for this. First I'll write a dummy node. Okay, so this I'll leave it blank. So this is the left child, this is for the right child, and this is for the boolean value. Okay, so initially this will be null, okay, and this will also be null, and this okay, you can either go for writing it as true or false, or else you can also go for using 0 or 1. Okay, we will use true or false, T or F. Initially this will be F and this will be F, and the first node which I am taking is this 10. Now I prefer inserting this 10 to the dummy node. Either you can go for inserting it towards the left side or towards the right side, it doesn't matter. Okay, let me insert it towards the left side of this dummy node. Okay, because just as a dummy node what we have created, just a dummy node, but actual nodes for us starts from here. Okay, and this root node, either you can go for inserting towards the right side or to the left side of the dummy node, but I always prefer using the left side. Okay, now from here I'll insert my root node 10. Sorry, this one I have to write like this. I think I erase it. This is 10. Okay, and now since the left tree we are writing, left subtree for this dummy node, so this I'll be making it as true, and this I'll be making it as false, because there is no right. And now this is the left child for 10, this is for holding the address of the right child for 10, and this is for the true and false. Okay, next is 8. 8 again should be inserted as the left subtree, left child for 10. Okay, eight I'm writing here, and this one, okay, I'll make it as 1 since the left child exists. So I'll make this as 1, and from here it is pointing to this, and this is the left child. This is for holding the address of the left child of 8. This is for holding the address of the right child of 8. Okay, now so what about the right child for 10? Yes, right child also exists for 10. Okay, now what I'll do now, I'll make this also as 1, and the right child for 10 I'm writing now, that is 12. This is for holding the address of the left child of 12, holding the address of the right child of 12, Okay, and now it is pointing here. Now is there a left child for 8? Yes, it is there. So this is 6, which is the left child. So this is pointing here, and then this is for holding the address of the left child of 6, and this is for holding the address of the right child of 6. And since the left child for 8 exists, this I'll make it as 1. Is there a right child for 8 also? Yes, right child is also there. So this one I make it as 1. True, that means the right child for 8 exists. Now this one is 9. And this is for holding the address of the left child of 9. This is for holding the address of the right child of 9. And okay, something like this. Now 12. Okay, so is there a left child existing for 12? Yes, it is existing. Now I don't have space. I'll try to write here below. Since the left child exists, this is also made as 1. And this is 11, and this is for holding the address of the right child of 11, address for holding the address of the left child of 11. And okay, let us come to this now. Whether there is a right child for 12? Yes, right child also exists. So right child is 14. This is for holding the address of the right child of 14. This is for holding the address of the left child of 14. So, and this is pointing here, and this is also made as 1. Now time to create the threads. Okay. Now you can just observe now. So this is set to false here. Okay. That means this is a null pointer now. So OP people are following. So what I'm talking is with respect to the dummy node what we have created. Even in the dummy node, see here. All of you can see this. Yeah, this is null pointer now. So you should not have the null pointer in the threaded binary tree. Now what we do, we create a thread to itself. Okay, so we create the thread to itself. Oh, okay, let me write it in the dotted line. So all threads, let me write it in the dotted line. It points to itself. Next, here I cannot create any thread because this is 1, this is also 1. Here also I cannot create any thread because this is 1 and this is also 1. Here also I cannot do. But here, see, there is no left child for this. That means this is okay. I am using true false. Sorry, I have changed it to this is true. This is true. This is true. This is true. Now it is false here. There is no left child for 6. There is no right child for 6, false. Similarly for 9, similarly for 11, okay. So I put false everywhere because there are no left childs or right childs for all these nodes. Now this is a null pointer. Now I have to convert it into a thread 6. So what is there before 6? Because it is the left child, left link, you know, there is nothing. Now from here I should be going for creating a thread to where? The dummy node. Correct? And next, so this is also from here it is going, and the right link of 6 is also a null pointer. Now after 6, what do you have? 8. That means you have a thread from here to here. Okay. Next, take the left link of 9. So you have 8. That means from here there is a thread to 8 again. Okay. Then take right link of 9. After 9 is how much? 10. So goes to there is a thread from 9 to 10. Okay. Now if I take the left link of 11, 10, it goes to 10 again. So from here there is a thread to 11. So write carefully. Oh, sorry, thread to 10. Okay. Okay. Now from the right link of 11, a thread to 12. All dotted lines are the threads. And now 14 left link is okay. Left link of 14, from left link of 14 you'll have a thread to 12. Okay. Now from the right link of 14, where it should go? To the dummy node, because after towards the rights of 14 we don't have 14, we don't have anything in the in order traversal. OP people understood with this? Okay. So this is how you got to write it. Okay. Construct the binary tree, threaded binary tree using the memory representation. Okay. This is how you got to do it. Okay. So yeah. I think I'll give you one more example. Yeah, one more example I'll give you. Try to do it. So all of you copied this. Shall I discard what I've written here? Okay. Yeah. Take this. These were asked, the question which I solved earlier and the question which I am giving now, these were asked in the previous question paper. 10, 20, 30, 40, 50. Yeah, do for this. So first construct a normal binary tree with a dummy node. Write in order traversal for that, then go for constructing the threaded binary tree. It will be easy for you. Start doing. Started doing. Okay. Finished? Okay, so dummy node I'll make it as D, and then 10, and then 20, and then 30, and then 40, and then 50. So tell me the in-order traversal of this. Hello? What is the in-order traversal of this? Hello? So 10, 20, 30, 40, 50. So 10, 20, 30, 40, 50. Yeah. So create a dummy node. Okay, let me write it towards the left side because we don't get the right subtree. So this is the dummy node. Okay, this I'll make it as false, this I'll make it as true, and I'll make 10 as the left child for dummy node. Okay, next there is no left child for 10. This is false, this is true, okay. Now here it is pointing to this. Next again this is false, and the right child for 20 is 30. And again this is false, this is true here, this is also true here, 40. This is false again, 40. This is true. Now we have the last one, 50, 50, and both are false. Okay. Now here, since we have, say this is a null pointer, make the pointer itself, and then this is null pointer here. Before 10 you don't have anything, so it should point back to the dummy node. And then this is null pointer here, so before 20, so there is 10, so from here it points to 10. Okay, so from here to 10, and then null pointer here again, so 30 before is 20, null pointer here, 30, 40 before is 30, so null pointer here, 50 before is 40, but null pointer here also, they should point back to your dummy node. All of you written the same? Okay. Okay, next is, So if you have copied, I'm discarding this now. Okay. Okay. So next is, so constructing the binary search tree using the traversals. So I'll give you the post order traversal, I'll give you the in order traversal. Now using those two, you should go for constructing the binary tree. Okay. So let me write the post order traversal. See, for constructing the binary search tree, in order is must. Okay. See, post order is given, pre order is given. Can you construct a binary search tree? It is not possible. Correct. So if you want to construct the binary search tree from the given traversal, so in order must be there. So post order is given, in order is given, you can go for constructing. Or pre order is given, along with the pre order, in order is also given, then you can go for constructing. Now first we will try to understand how to construct the binary search tree using the given post order traversal and in order traversal. Later we will try to understand how to construct the binary search tree using the pre order traversal and in order traversal. For both, in order traversal is must. Okay. So let me write some post order here. POST, post order. So post order traversal is this. I'll write here H I D E B F G C A. This is the post order traversal of some tree. Okay. H I D E B F G C A. And similarly, the in order traversal is this. I'm writing the in order traversal now. H D I B E A F C G. Write these two sequence, all of you, in your rough note or classwork or in a sheet of paper. Written? Okay. See now, first what we need is the root node. Now from where can you find the root node? See, post order is given, in order is given. So can you people just open the examples which we have solved, traversing the tree, given tree, traversing you have done, and you have written the traversal also. Just look into the post order, okay, the post order traversal which you have written for some tree. What will be the last node of the post order traversal always? It is the root node. Now, from this given post order traversal, I came to know that A is the root node of the binary search tree. Okay, people understood? Okay. Yeah, I'll make A as the root node. A I have made as the root node now. Next, so I got to find out which nodes will come towards the left subtree of A and which nodes come towards the right subtree of A. And to do that, so you got to observe the in order traversal. See, A is here. A is here. Correct, right? So the root node A in order traversal is located here. All the nodes which are towards the left side of A, can I know? All this H, D, I, B, E. These are the characters or the nodes which are towards the left side of A. So they will take the left subtree of what? A. And all the nodes which are towards the right of A, that is F, G, G, they'll take the right subtree of A. Okay, now I have found out. So what are the nodes that will be coming towards the left subtree of A, and what are the nodes that will be coming towards the right subtree of A. So now I'll just mark it. And we got to expand it further. Let me write it. H D I B E. So all these nodes, they will occupy the position left subtree of A, and similarly F C G, they come toward the right subtree of A. Correct, no? Now again, so just try to look for this sequence. Okay, see, I have written H D I B E, correct, no? So and try to find these characters in the post order. See, H is here, D is here, B is here, E is here, and I is here. Now what I'll do is I'll try to go for sequencing these characters as per this. See, it is the same set of characters what I'm saying here, H D I B E, and this is also H I D E B. That a little different. The sequence is little different. What I'll do now, so I have found that H D I B E, all these nodes, they occupy the right left subtree of A. So I'll just go for sequencing them appropriately. So let me sequence them properly. How? H. I'll sequence them such that it matches this sequence. H I D B, E, and then B. OP people understood what I am doing? So I found that these are the nodes that will be coming towards the left side or the left subtree of A. Now same thing I have written, only thing is I have sequenced them appropriately such that it matches a sequence in my post order traversal. Is it clear? Okay. Now when I try to look for this sequence in my post order traversal, this is the sequence. Correct, no? In this sequence, so which is the last node again? So just don't take this into account. So take only the sequence. In this sequence, which is the last node? B. Now the left child of A will be what? B. So let me write it again. Okay. So this is the first step what I have done. In the second step, I write A, and then among these nodes, I found out what is the left child of A, that is B. B is here. Correct? Okay. Let me finish with the left subtree first, and then we will focus on the right subtree. Okay. Now B I have found. B is the left child of A. Now if I look into the in order traversal, okay. Now what is there towards the left side of B? HDI. Okay. So HDI will form a left subtree for B. H D I. Get it? And in this sequence, towards the left side we have HDI, and towards the right side of B. So what is there? So only among this sequence you have to find. In this sequence, toward the right side you have E. So that is the only thing. So that means I found E is the right child for B. Okay, people are following? Okay. Now in this HDI, I got to find out which is the left child of B. How to do that? Again, now I got to arrange these characters in the as per the sequence it matches with the post order. See, HDI, here also I have, HID I have. So I'll go for sequencing it. H, so same characters, but I sequence it as per the post order. HID. Understood? This is D. This is D. HID. Now again in this, now when I look into the post order, among this HID sequence, which is the last character? D is the last character. Now D will be the left child for the node A. Okay, let me write here. So this is the first step what I've done. So this is the second step what I've done. Now I'm doing the third step. A is the root node, that is fixed already, and B is the left child of it, that is also fixed. And now I came to know that the left child of B is D, and the right child of B is already fixed, that is E. Okay, now I have two things remaining, H and I. Okay, let me write. So H and I use rectangle for writing H and I. Okay, again I look for the sequence HI. Okay, the same sequence HI I have found here. Now what will be the in the same sequence, since there are only two characters, in the fourth step what I'll do, so this H will be the left child of D and I will be the right child of D. Okay, so A. Okay, people are following? So in case if I have three nodes or three characters here, I got to decide which one is the root. Okay, now there are only two, H and I, and in the same sequence. See, post order, if I look here, H first and next I next. What does it mean? H is the left child and I is the right child of D. B, and then D, and then E, and next is H is the left child of D and I is the right child of D. Correct? And similarly, you got to do it for this also. And there are only three characters here. First thing, you got to find out which is the root. Let me sequence this FCG. Okay, as it is in the post order. So here I have it as FGC. Let me write it as FGC. FGC. So the C is the last one. That means so the right child for A is C. Get it? And after writing this C as the right child of A, there are only two things remaining, F and G. Okay. So again, you don't have to go for detecting the root node. So F will be the left child of C and G will be the right child of C. F is the left child of C and G is the right child of C. So OP people understood how to construct the binary search tree from the given post order and in order traversal. Okay. So I will give you one more example. Okay. Try to do that. So tomorrow we will understand how to construct the binary search tree from the given pre-order and in order. Okay. So I'll give you one more example. Have you people copied this? So if you people have copied this, I'll discard this. See, in order is must, in order is required. Without in order you cannot do. Okay. Just try to solve this at home. Construct the binary search tree for this. So I'll write post order plus first post order traversal is this. I'm writing here I E J F C G K L, sorry, this is K L H D, B, A. So this is the post order traversal, and in order traversal is E, I, C, F, J, B, G, D, K, H, sorry, after D it is K, H, L and A. Okay, so copy this and try to construct the tree out of this. Okay, binary search tree. It is easy, you can easily do it. Only thing is, after finding the root node and all the nodes which come towards the left side of the root node and towards the right side of the root node, after writing, you should go for sequencing it as it is in the post order. Sequence it and you again take the last node in that sequence, that will be the left child or the right child. So the same thing you have to keep doing until the tree is constructed. Is it clear? Okay, so we'll stop here, and tomorrow I'll show you how to construct the binary search tree using the pre-order traversal and in-order traversal. Okay, yeah. So copy the sequence.